Okay, so we're going to look at several different applications. Some of it we started looking at last time itself. And we want to continuously kind of connect the model of the received signal that we'll be studying in the context of what we have done for CT, what we have done in CT516, where we took a view of the modulated signal as forming a vector in a multidimensional space, and the basis of that multidimensional space had a lot to do with the design of the modulation scheme. Over there, we took these basis vectors as entirely orthogonal to each other and having unit length. In a lot of these different applications, for example, beamforming, which actually is not only spatial domain, but also temporal domain filtering design as well, as we have seen in the earlier lectures. Or if I do code division multiple access, at least for the synchronous case, for MIMO, and a general problem of deconvolution. In all of these problems, what we will see is that our input, the received signal, can be written in a manner which is quite analogous to the vectorial format of the modulated signal that we have seen. The only difference, actually the main difference, is that these basis vectors, the basis functions, they cease to be orthonormal. And that creates actually all sorts of problems. Not if the signal to noise ratio is very high. In a very high SNR environment, even when the basis functions are not orthonormal, it is not as much of a problem. But in the typical operating scenarios where SNR cannot be assumed to be high, then the loss of orthogonality is the main challenge that has to be overcome. And that is where we will be focusing our attention on. So we will be looking at these 4 application areas, and then we will summarize and kind of unify these 4 different topics. And actually, these 4 are the ones that I have listed here. There are actually several other problem formulations which can also be added, for which this unified summary is applicable. So I think the content of this lecture, this topic, is highly, it has a very vast domain of applications, and I think you will be equipped to solve a wide variety of problems using this study that we'll be doing. Now, in this lecture, the focus will be on solving these different problems using linear techniques. And specifically, we will be considering 2 different techniques, least squares and minimum mean squared error estimation. I believe that most of you, if not all of you, are familiar with this LS and MMSE, but it will be probably still useful for us if we do kind of a quick review of the idea behind these techniques, the mathematical principles or the concepts of least squares and MMSE. And so we will be doing that both from a geometric viewpoint, where we will try to get a geometric understanding of what the least squares is doing and MMSE is doing, as well as a calculus-based approach. And for MMSE, we will be actually also looking at a statistical approach, which I still haven't added in this slide, so it doesn't show up in this table of contents. So this is the range of topics that we'll be covering as a part of this set of lecture sessions. Okay. So for beamforming, we have already seen this system model, which is summarized in equation 1. And we have seen that the same equation, same system model is also applicable when I try to form the discrete Fourier transform of a signal with multiple uh, re received signals. So when I take discrete Fourier transform, or if I'm doing beamforming, especially let us say with uniform linear array, these column vectors become nothing but complex exponential signals with different frequencies, f0, f1, up to f of k minus 1. Okay, so this is the model that we have already seen. And in the context of this model, what we have assumed is that the incoming signal is a composite of k different transmitters, which are all interfering with each other because they are all being received at the same nominal frequency. And we would like to estimate the transmitted symbol vector given the received vector x. I think last lecture we also took a view of this particular equation number 1 on the previous slide as a generalized modulation symbol. The only difference is that the coordinates of that constellation point are being defined by different transmitters now. Plus, the coordinates are not remaining real valued anymore. They are actually possibly complex valued if different transmitters are, for example, sending QPSK signal, then we have to consider this as a complex valued hyperspace rather than a real valued multidimensional space. But other than that, as I said at the beginning, we should be able to kind of directly extend the concepts that we had studied in CT516 for the modulation topic and apply them to this equation 1. So when we talk about beamforming, this is actually what we are trying to do. We are getting this received signal and we are assuming that we know this matrix capital W, and now we are trying to recover the transmitted signals. So that is a general framework of beamforming. Or it can be also called a source separation problem. And maybe the difference between beamforming and source separation, what I would say is that in the literature, in the papers, technical papers, when the authors talk about source separation, they are not necessarily assuming that those column vectors, WF vectors, they may not be necessarily the complex exponential signals that we have seen in the earlier lectures. They may be experiencing, for example, some type of fading while getting transmitted in the wireless channel. So equation 1 remains the same, except the structure of those columns may differ in this source separation problem. A lot of the times we will assume that those column vectors are known at the receiver. At least that is the assumption moving forward. And if it was a beamforming problem, and all that we would need to do is estimate the direction of arrivals. Because once we know those direction of arrivals, we know that the individual WF vectors are just complex exponential functions of that direction of arrival. So in the beamforming problem, in the FIR filtering problem, the assumption is that either the frequency of arrival or the direction of arrival is known, or it is estimated using one of the several techniques that you are studying as part of Lab 3. A lot of the times, even when the problem statement doesn't directly imply that the the column vectors are the complex exponential vectors, we still somehow assume that this matrix W is known. How it is known is not the topic of today's lecture, but that is the assumption that we are making. Practically, this knowledge will have some error, because anyhow this W is most likely going to get estimated, and that estimation process will induce its own errors, and we have to be careful about that. For today's lecture, we are assuming that there are no estimation errors. So we are actually taking a very simplified view. There's a whole lot of study that has been undertaken and that is still currently going on, where the effect of inaccuracies in the estimation of W are studied extensively. Okay, so with that, let us move forward. We have seen this correlation matrix of the incoming signal, where we take expected value of x Hermitian, and it ends up having this particular form. If suppose we assume that different sources are entirely uncorrelated, then this RSS will become a diagonal matrix. If we additionally assume that all of the sources, all of the transmitters are getting received at the same power, then it will be just a scaled identity matrix, where the scaling will be the power value that is being received, which is common for all the transmitters. And so what you will see is that this correlation matrix that we have looked at earlier is the outer product of W, which is W Hermitian, plus this noise term, which is again a scaled identity matrix. But the key point is that we are taking this RXX to be W Hermitian. In other words, when I do this W Hermitian, if you just do a simple math, what you will observe is that individual elements of this W Hermitian are nothing but the dot products between different rows of W. Okay. W has how many rows, by the way?
N.
It has n rows. And so therefore, there will be total of how many? Okay, my voice is breaking. Are you having problem in listening to me?
No, sir.
Okay, I will continue now. So Divya or Bhavesh, if you are having problems with my audio, just raise your hand, okay? And then I'll see what I can do. Okay. Okay, so when I do W Hermitian, that will be a matrix, and that matrix will have individual elements which are dot products between different rows of W. Okay, so this should be fairly straightforward for you to confirm. Now there are total n rows, and so there is total of how many unique dot products that I can take?
N square.
N squared is the total number of dot products I can take, but what will be the unique number of? Yes. Yeah, n choose 2, right? Now, what is that n choose 2 number? You will see that n choose 2 number forms just the upper triangular portion of this W Hermitian.
Yes, sir.
And that is why this matrix is the Hermitian matrix. The lower triangular is just a complex conjugate of the upper triangle. The actual unique values are only in the upper triangular part. The rest of the matrix can be determined from that upper triangular parts. Basically, what we are saying is that if I have, let's say, 10 rows in this W, and if I take dot product of the third row with the seventh row, then that will be the same as if I take the dot product of the seventh row with the third row after I do complex conjugation. Okay, so that is where the symmetry, complex valued symmetry of this matrix is coming from. But anyways, the point that I wish to make is that this is a correlation matrix, and the individual element of this matrix can be thought of as correlation between different rows of W. Right? When we take the dot product, the dot product operation in a statistical manner, we can consider it as an indication of correlation. When the two rows are perfectly correlated, which is what happens if you take the dot product of that row with itself, after necessary normalization, for example, after dividing the dot product by capital N, we get value of 1. The correlation value becomes 1, which means that a particular row is obviously perfectly correlated with itself. If a row is orthogonal to some other row, then that dot product will be 0, which means that these two rows are orthogonal to each other. And otherwise, all the other values of this matrix will be between the magnitude of the dot product will be between 0 to 1. Now, I think we did this last time. Instead of taking the dot product of one row with respect to another row, it is possible also to consider dot product of one column with respect to another column. And when we do that, we form another matrix that I have called here capital R. And here I didn't put this subscript XX. Maybe I should have put RW as a subscript, or W as a subscript and called it RW. But for the sake of notational simplicity, I am denoting this W Hermitian W as correlation matrix R without any subscript. So capital R is always going to refer to this correlation matrix. Maybe sometimes this W notation will become some other notation. Maybe we will call this W matrix as some H matrix later on. But this capital R always will mean that we are taking type of matrix product as indicated by equation 3. Specifically, individual elements of R are the correlation between the columns of this system matrix W. Here, there were the correlation between rows. Here it is correlation between the columns. Now, if I assume that the columns of W are linearly independent, then I can show that R is full rank, meaning that the rank of R is capital K. And when R is a square matrix and it has full rank, it is invertible. So in a lot of scenarios, we are going to assume that that is the case, that R is invertible. Now, what I would like you to think of on your own is, in order for me to say that R is invertible, why do I need to say that the columns are linearly independent? What happens if the columns are not linearly independent?
सर the determinant becomes
Singular matrix हो जाएगा. I mean, yeah, determinant will be 0.
Right. So when the columns of W are linearly independent, what happens to R? Why R ceases to have full rank? That is what I would like you to tell me.
When the columns are linearly independent, either one of the column becomes zero. A column or a row becomes entirely of zero, so it's not having the rank means the non-zero.
No. Let's say W has 3 columns. All the 3 columns are non-zero. But only the first and second columns are linearly independent. The third column is a linear summation of the first 2 columns. Okay, Nidhi said only diagonal elements are present, but no, not the case. Nidhi, the diagonal elements will be present only if each column is orthogonal to the other columns.
Sir, the determinant
We are
will
not saying that they are orthogonal. What we are asking is if they are.
Sir, if columns are linearly dependent, then either one of the columns can be written as linear combination of other columns. So if we do any kind of row transformation, we can again reduce the matrix to a rank which is less than k. So if it is linearly independent, so we cannot reduce any by any row transformation or any column transformation. So that's why the minimum number that is there to have distinct linearly independent column is so the rank is k.
Bhavesh, you are giving me an answer which uh, a pandit in linear algebra can understand. So all that I want to understand is why this W Hermitian W ceases to have full rank when W has linearly independent columns. My question is about this matrix R and whether it is full rank or not full rank. And I'm saying that if W has linearly independent columns, then somehow this R starts having rank which is less than capital K. And so that is what I was considering, that if W has 3 columns, and let us say first 2 columns are linearly independent, and so these 2 linearly independent columns define a plane. There's 2 columns, 2 vectors, and they're linearly independent, meaning that they are not pointing in the same direction. So one vector might be pointing at some 30 degree and other vector might be pointing at some 70 degree. So if I look at those 2 vectors, they collectively define a plane. Now, I would like the third column of W, and I'm saying that W has only 3 columns. So I would like the third column of W to be going in third dimension, which is not along the plane. So the 3 columns of this W matrix, I would like them to define a 3-dimensional space. And then I'm okay. Then this R becomes a 3 cross 3 matrix whose rank is also 3. And so it is invertible. What I'm asking is, if in case this third column ends up being on the same plane which is defined by the first 2 columns, then this matrix R is rank deficient. It has a rank of only 2. And I'm asking the question regarding that. Why does the linear dependency of the columns of W end up making R, which is defined in this manner, why does it end up make R rank deficient matrix? That is my question. So I'll let you think of it, think about it on your own. But now take it as, yeah.
Sir, we can look at it like the eigenvalue corresponding to that third dimension will become 0. So the determinant will become 0.
Yeah. So yeah, if you get into eigenvectors and all, yes, that is one way to possibly answer this question. But why does eigenvalue become 0? And that becomes a question. Yes, I know we have studied that as one of the properties of our eigenvector analysis, but I mean, maybe again, like what Bhavesh was getting to, your answer is correct, but it makes use of a concept that is maybe more complicated than what it needs to be.
Yeah,
So,
sir, I was also thinking in terms of row echelon transformation. Like if we transform,
yeah, yeah. So try to get an answer which is as simple as possible. But anyways, let's move forward. As of now, we are going to assume that these columns are linearly independent. And now we will perform this linear operation on our received signal vector x. Remember, I have said that this W is known. So I can take that matrix and do a Hermitian transpose on X. Remember, the dimension of X is n cross 1 and W is n cross k. So I can't do W times X because the dimensions won't match, but I can do W Hermitian times X. Essentially, when I do this W Hermitian times X, it is as if I'm trying to correlate X with different columns of W, right? So there are total of capital K columns, and so I'll get total of K correlation outputs, which I'm collecting in this vector Y. I can write this vector Y by expanding out the formulation of X as W Hermitian W S plus W Hermitian U, which I have denoted as this vector V. But recall that W Hermitian W, we have defined it on the previous slide as this matrix R. Okay, so I can do this linear transformation. Now, what you will notice is that because we have assumed that the number of simultaneous transmitters is less than capital N, this Y is smaller in length compared to X. So it is easier to deal with. I don't have to deal with as many numbers anymore. I have to deal with a collection of K numbers instead of N numbers. So that is some benefit. But it's not just that this reduced dimensionality is numerically or computationally it is better, or it is better in terms of the memory requirement, but I don't give up anything by just taking a look at Y. Meaning that if I throw away X after performing this operation, if I throw away X, then I do not lose any information whatsoever. The reason is that suppose I throw away X and then later on I have a change of heart and I feel, oh my God, I really didn't mean to do that. Then, well, I know W and I know Y. So I can recover X from Y. Okay? At least in the noiseless case. In the noiseless case, all that I will need to do is multiply Y with R inverse. So anyways, so this is in some terminology, it is called sufficient statistics. So this vector Y provides the same type of information that vector X provided because R is invertible. And then what we can say is that if I have Y, and because I wrote Y as R times S plus some noise vector, and I have said that R is invertible, I can get the estimate of the symbol vector S by just doing R inverse times Y. And so I will get S plus R inverse of V. So this is known as the least squares solution. It is also sometimes called decorrelator. Y has correlation present between different elements of S. And that correlation is coming because of this correlation matrix R. And by doing R inverse, we are breaking away, we are breaking apart those correlations so as to get the original vector S back. Other way to say is that the vector Y, or in general vector X, is suffering from interference. And now by doing this operation, we have actually perfectly removed the interference. This S, we have recovered completely back. The only problem is that I also have this R inverse of V term, which is a noise term, which is going to be there. But in absence of noise, in the high signal to noise ratio scenarios, I can say that I have done the task of interference cancellation in the perfect manner. So at this point of time, let me take a pause and ask you, how is this different from what we did in CT516? Equation 4 and equation 5. Remember, we started this lecture by saying that everything that we are doing here can be thought of as a generalized or maybe more complicated version of the basis vector formulation of modulated signal that we have studied in CT516. So what I'm asking is, can you tell me what is the counterpart of equation 4 in CT516 modulation or demodulation framework that we had last semester, the last lecture?
This W was F, which was our column-wise basis vectors, and we used
Yes.
F admission F S, and so there
Yes.
F was orthonormal, but here we have to take inverse, like inverse operation instead of permission, because
So just say what will be 4 in the context of CT516.
sir, this received signal would be F Hermitian F times S plus
What
noise.
what will be equation 4?
Uh,
Equation 4, let us look at y. Y is equal to Rs plus V. What will be R in the demodulation context?
F Hermitian F.
And what is that? Arushi said 1.
Identity matrix.
Yeah. So Arushi, it's not a scalar. F and F is a matrix. So F Hermitian F is a matrix. But maybe what you're saying is correct. The point is valid that only the diagonal elements are going to be 1. All the non-diagonal elements are going to be 0. That is the definition of orthonormality of columns of F. And there F was in our control, so we purposefully designed it that way. Yeah, so basically at the demodulation, in the demodulation operation that we studied in CT516, we were actually doing equation 4. The only thing is that this capital R was turning out to be identity matrix because all the correlations between different columns of W were intentionally designed to be zeros. And so by doing this operation, we were directly getting equation 5. We didn't have to do this R inverse again because R is itself on the identity matrix. So if I do inverse of identity matrix, it's a trivial operation. It's the same thing. So we were getting equation 5 directly by equation 4. Basically, equation 4 was same as equation 5. Except there is one problem here, which is this term. See, in at the QPSK or POM or Emery orthogonal modulation schemes, because the basis functions are orthonormal, I don't have to do any matrix inverse at all. Here, because the basis functions are not orthonormal, I'm forced to do this R inverse. And when I do this R inverse, my noise vector V gets multiplied also by this R inverse. I get the signal portion back completely uncorrupted. So all my interference is removed. The price that I have paid compared to CT516 framework is that I kind of am messing around with the noise vector here. And the reason I say it is sometimes not a good thing to do. Sometimes it is going to give me acid burns, is because this R inverse, remember R is the correlation matrix. And I don't have full control. I can't control the values of those correlation terms. By the way, are you able to hear me? Am I audible?
Yes, sir.
Yes.
Okay. So what happens is if this matrix R starts having columns that are, I mean, first of all, we have assumed that R is full rank, so I can at least take inverse. But sometimes a matrix can be full rank, but still it may be ill conditioned, meaning that yes, its column vectors are going to be occupying the full k-dimensional space. Okay, so Anudeep made some comment. What was the comment? Elements of R are between 0 to 1, so elements of inverse can be greater than 1, so there will be increase in the noise power. Yes. So that is one quick way to summarize it. But maybe generalizing what Anudeep was saying, if elements of R are between 0 to 1 doesn't mean that all the elements of R inverse will be greater than 1. Some of them will be maybe less than 1. But the problem is that if the columns of R are not nearly 90 degrees apart, let's say R has maybe 3 columns. First column is, let's say, along X direction, other column is along Y direction. So they are nicely 90 degree apart. But the third column, instead of pointing in the Z direction, it is making only 1 degree angle with respect to XY plane. If it was on XY plane, then I can't even do R inverse, because then R becomes non-invertible. It will have rank of 2 instead of 3. But now I'm saying that R is invertible, but except wait, my third column is only making 1 degree angle with respect to this horizontal plane defined by the first 2 columns. Then technically R is invertible, but when you try to invert R, you will start having some elements at least which are very, very large, which is sort of like what Anudeep is saying. And those large values of R will amplify this noise. Okay, so that is the price that we pay compared to the ideal case in which R is the identity matrix. But if we say that we are operating in a very high SNR scenarios where V is anyhow very small, maybe it doesn't matter as much. So at least in the absence of noise, we have solved this kind of complicated problem where we are getting a signal which is a jumbled up mix of many co-channel transmissions, but we recovered the original values back. Now, the other question I will ask you is, what happens if capital K is 1? Sometimes capital K is not 1, but then there are some receivers which are known as single user receivers, which just kind of raise their hands and say that we are going to just assume that capital K is 1. All the other K minus 1 transmitters, I'll just dump them into this vector U. I'll consider all of the other interference that is impacting me. I'll call it as noise. So that is what is known as single user receiver. But let us not consider that other case. Let us just assume that K is actually indeed 1. Then can you tell me what happens to this 4 and 5, equations 4 and 5? Correct. So R will be a scalar, right? And so now this will be just dividing Y by just a scalar. What will that be called now? Okay, Priyanjali.
Scaled version of Y.
Yeah, no. That is fine. I'm asking. There is a term for this that we have, I think, used earlier. What is the term? When capital K is 1, when I do this W Hermitian X, what am I doing?
Projecting WH over projecting X over WH.
Right. But remember, my X has a signal component with also W. W is a vector. And so when I do that projection, that type of projection has a very specific terminology. I'm not projecting X on any arbitrary W. I'm projecting X on this model W of the transmitted signal. So when I, instead of taking any random W, if I project X on the specific W that makes up the transmitted signal, then what is that operation called? Okay, it's called matched filtering. Okay, you probably have heard of that term. The reason it's called this, when we say that we are doing projection or we are doing correlation, there is other word for it which is also kind of general, which is that we are doing some type of filtering. I mean, when we think of filtering, it is, remember, always in terms of convolution operation. But an individual output of the filter is nothing but the dot product between the incoming signal and the filter vector, the impulse response of the filter. So in that sense, if I look at one individual output of the filter, it is nothing but the dot product. Now, when I say capital K is 1, what will be Y? Y will have a dimension of?
One cross one.
Yeah, so it's a scalar.
No.
So it is one individual, I mean, we can think of it as a one individual output of a filter. Right? So in that sense, whenever I do inner product, I can kind of think it in many different ways. The projection is one way, which is the linear algebraic way, where we don't bring in any signal processing or even machine intelligence at all. When we think of that projection operation as defining a correlation, we are talking maybe about ML, AI theory or signal processing theory. And the third way is to think of it as forming one output of a FIR filter, and that is purely a signal processing point of view. And when we form the filter output using same W as the W that is used in our signal model, it is called matched filter. So this decorrelator for a single user case is nothing but the match filter. Okay. So let us pause here for just a moment, and then I'll be back in a while. Okay, so I'm back. I want to ask you now, suppose I have a matrix like this. Okay, it's the simplest matrix. One is along the diagonal and X is on the off diagonal. What will be the inverse of the matrix? By the way, my screen is visible?
Yes, sir. So we can put, instead of x, we can put minus x and divide it by 1 minus x square, this entire term. This entire, each element divided by 1 minus x square. And
Yeah. Okay, so that is all I wanted. So the determinant of this matrix will be 1 minus x square, and so it will, the inverse, whichever way it looks like, it will have, in the denominator, it will have a term 1 minus x squared. Is that fine?
Yes, sir.
Okay. Now, let me go back to this. So let us say that capital K is 2. Here we considered K is equal to 1. By the way, this screen is visible now?
yes, sir.
Okay, so let's say capital K is 2. Then what will be R? What will be the form of R when capital K is 2?
2 cross 2.
2 cross 2. What is going wrong with my letters? Just hold, okay? Okay, sorry for some, I was having some technical difficulties. Okay, so R will be 2 cross 2, yes. But what will be its form? Okay, so Anudeep says, okay, it went away. Anudeep had some answer. Let me see what it was. Right. So yeah. So Anudeep says that R will be. Sorry, no. This is Arushi. Arushi says that R will be same form as A. Yes. Yeah, Arushi. So it will be same form as A, But is one small change I'll make is that in general, when we say that the columns of W are complex valued, in A I had X on the off diagonal. It was the same X. When the columns of W are complex valued, the one of the two values will be X conjugate. But yes, if columns are real valued, then it will be same form as A. Now, remember when we say, when we define the correlation matrix, especially in the normalized sense, which is what we are going to assume, then the highest value will be 1. A particular vector can be maximally correlated with itself. And if that correlation is 1, I cannot bring in some other random vector and try to get a correlation which is bigger than 1. That doesn't happen. And actually there is a proof, mathematical proof of that. It is called Cauchy-Schwarz inequality. So basically in that formulation, X will be a value between -1 to 1. Or in general, if we say that X is positive, then it will be some value less than 1, between 0 to 1. So Joel pointed out that when I try to take the inverse, there'll be 1 minus x squared term in the denominator. And so now suppose that this correlation, which we are now calling it to be X between two columns of W, is pretty high. It can never be 1. If it is 1, then all bets are off. We can't even do R inverse. Because then these two columns are linearly dependent on each other. I mean, they are pointing in the same direction. So this correlation is not 1. I mean, sorry, the value of X is not 1. But let us say it is 0.9. Then what I have in the denominator is a value like something like 0.19 or something. So 1 divided by 0.19 will be some large number. And that is the reason why there is this problem of noise magnification. If instead of 0.9 it is 0.99, then 1 minus x squared will become even further closer to 0. And so 1 divided by that will be some really huge number. Does it make sense?
Yes, sir.
Okay,
Sure.
so in that regard, we will now bring in another method, which is known as the minimum mean square error solution. And oh, by the way, both of these techniques, least squares and MMSE, they are highly relevant to the next generation systems, although we haven't applied them to the next generation communication systems. But whenever we talk about MIMO or whenever we talk about non-orthogonal multiple access, these techniques are currently being applied. So this is very like today's topic. It's not a topic which is relevant 10 years back. Okay. So MMSE solution is written like this. So why it is like this, we will get to it later on. But as of now, you just take it from me that this is how the MMSE solution is. So MMSE solution is very much like least squares. It still makes use of the same vector y. And because y is, as we said, it contains all the information that we need anyhow. So it uses y. It also uses r. And it also does inverse operation. So in a way, it is a lot like the least squares. But one little thing that it does, which makes sometimes all the difference, is it puts this diagonal term. Where this terminology is very commonly used in the literature. It denotes a diagonal matrix. And the elements along the diagonal are given by what is inside this curly bracket. Here I'm saying that the elements along the diagonal are the signal to noise ratio of these different users. How do I define signal to noise ratio for the kth user? I just take the power of the kth user and I divide it by sigma square u. What is sigma square u? It is u Hermitian matrix, which is assumed to be a scaled identity matrix, and the scaling term is sigma square u. What this means is that this u vector is assumed to be uncorrelated. What is this u vector again? Let us go back. It is this vector here. This vector, u, original noise vector. Not v, not after it gets scaled by R inverse. This is the original u vector that we have considered. And so if I assume that to be kind of temporally or spatially uncorrelated, meaning different samples of vector u are uncorrelated, then if I do this operation, I get a scaled identity matrix. Sorry, this should have been identity matrix of size n. This is a typo. This we have actually, we should have used it here also, right? Yeah, this one. Basically, this square u is defining the power of the noise, and therefore, if I take the variance of the signal divided by the power of the noise, I get the signal to noise ratio for the particular user. I have a total of k users, and so this diagonal matrix will have k elements. What we are doing is the individual element is not the signal to noise ratio, but it is noise to signal ratio. It is the inverse of signal SNR. Okay, so that is the difference between the least squares and MMSE. But it sometimes, as I said, it makes a lot of difference. So let us see. Let us consider some specific cases. Okay, so one case that I will consider is that the SNR is very high, meaning that all the users are being received at a power which is much, much greater than sigma square u, meaning individual gamma terms here are like 1,000 or 5,000 or something like that. Then what happens? What if SNR is very high?
Sir, then the difference between this MMSE and least square will be like very small. Like it will, MMSE will tend to least square.
Correct. So at high SNR scenario, this diagonal term will start becoming 0. And so S hat will just become R inverse Y. So again, as I said earlier, if SNR is high, if this U term can be, this V term can be ignored, then you can't do anything better than the least squares. But if signal to noise ratio is not very high, then there is going to be this diagonal term. Now, suppose this R, this matrix R, is ill-conditioned. We took this example that it's 2 cross 2 example where the values are 1, let's say 0.99, 0.99 and 1. Those 4 values make up this matrix, correlation matrix R. And we said that in that case, there'll be a significant noise enhancement. But now let us assume that the SNR is pretty low. I mean, well, not pretty low, but it is not as high as 1,000. Maybe let's say it is 10. So this diagonal term will have values which are around 0.1. Now, what happens is that if I do that matrix 1, 0.99, 0.99, and 1, and even there, if I add 0.1 along the diagonal, so 1 becomes 1.1, then inverting that matrix becomes easier. The denominator starts having values which are not very close to 0. And so the noise amplification reduces. So basically, where MMSE starts outperforming the least squares decorrelator is where R is not identity matrix and SNR is not very high. Let us consider one more example that R is not even full rank. When R is not full rank, I cannot even do this. Least squares is out of the window. But I can still do MMSE because I added this diagonal matrix, and in the presence of diagonal term, the composite matrix is guaranteed to be invertible. So a problem which is not solvable by the least squares technique becomes possible to solve if we apply MMSE. And then finally, consider one other case that SNR is very small. So when SNR is very, very small for all the users, it will be as if this matrix R is not going to matter too much because this diagonal 1 over gamma will be very high. And so at that point of time, the MMSE says that forget about R, just take Y and scale it by this diagonal 1 over gamma S term. In a way, it makes sense. If SNR is very small, the signal is almost not present. And so we are pretty much getting the noise through. And that is what the MMSE is telling us. So MMSE is a little more smarter than the least squares. It kind of gives us some type of tuning control. And that tuning is happening across the diagonal elements of R. We can almost say that we are adding some values along the diagonal of R. How much to add along the diagonal of R is determined by the inverse of the individual SNRs. And the amount that we add to the diagonal of R makes this matrix inverse to be better conditioned compared to least squares. The only limitation of MMSE is that we need to know this signal to noise ratios. If we don't know what those signal to noise ratios are, then we can't actually do MMSE. But one approximation that is still used is to say that, yes, I don't know what signal to noise ratios are, but I'm just going to assume that there are some values. I'm just going to assume that they are all, let's say, 1. All the SNRs for all capital K users is 0 dB, 1, a value of 1. or maybe I'll assume that it is 10 or 100. I may not have exact knowledge of what SNR levels are, but maybe I know it in a ballpark range. Maybe I know that the values are around 1, or maybe they're around 10, or maybe they're around 100. Maybe I know it in the order of magnitude scale. Then I'll just put those values here. Most of the time in that case, all the values are constants. And so this a matrix becomes the identity matrix scaled by either 1 or 10 or 1 or 0.1 or 0.001, like that. And then this is not really truly the MMSE, but it is sort of like MMSE, because we are just making up the SNR levels. In the outside world, in the, for example, machine learning community, this is known as regularization. Basically, the engineers and algorithm developers, whenever they come across a matrix R which is non-invertible or invertible but very poorly conditioned, they just put a diagonal term to it, and so it becomes invertible. And that is known as regularization. And I think Joel and Anudeep are familiar with it. They have experimented with this regularization method, and it works. The problem which is not solvable becomes solvable once you regularize it, which is to say that we are doing some type of MMSE. Okay, let me do one last thing today and then we'll conclude. So here I'm going to describe a way of doing beamforming or even FIR filtering, which is little different. If I just mentioned names of Joel and Anudeep, and so I will again say that if you think that this is some esoteric topic that I am bringing up, that is not having practical relevance, just go and talk to Joel and Anudeep, because this is what they have been doing for past so many months now. We want to compute the beamforming weights in an offline manner. Remember, here we are doing everything online. We are getting some signal X, and using that signal X, we right away are forming Y, and then that Y we are multiplying with this R inverse. On the other hand, here we are kind of trying to compute the weights, the beamforming coefficients in this vector W in an offline manner. And all that we have is some type of requirement or a specification that we want to filter out the interference coming from a specific frequency in case of the temporal filter, where we, for example, know the frequency of arrival, or null out the interference coming from some specific directions in case of the antenna arrays. And so we are given this specification in terms of what is known as stop band and the pass band for the FIR filter. For the beamformer, these specifications are provided in terms of the beam shapes. We are given some beams. We are told that, okay, we have to form a beam over certain region. And when we do that, additionally, can you please cancel out the interference that is coming from some other geographical region? So now, instead of frequencies, we are talking about the directions of arrivals. But as we have seen earlier, they both are mathematically equivalent statements of the problem. So how to do this now? Ultimately, we want to form a beamformer, and so it's going to be some type of inner product operation. And that inner product is going to be implemented by this vector W. It is same vector W that we have formed here. But I will let you figure out how we are doing W here, okay? I'm not specifically going to write it. Maybe that is something that you can think of until we meet next time. That in this method 1 and method 2 that we have defined here, what is the beamforming weight vector W that we are now looking at? But here we are kind of specifically trying to find out what this W is. That is the vector of either filter coefficients or the beamforming coefficient, and this vector W should be such that our specifications are met. And so then we have to mathematically write down the statement of the problem, and that we are going to define using a matrix H. We are still having exactly the same mathematical model, that either there are different frequencies coming at different frequencies of arrival, or different signals are coming at different directions of arrival. And so the either the temporal vector or the array vector is still going to be the complex sinusoidal vector. But we are now going to define it in a slightly different manner. So that is why instead of using the notation capital W, I have used a new notation, capital H. Okay, so let us say that N1 is the number of frequencies or the DOS at which the filter or the beamformer is going to pass the signal without distortion. And so we are going to make up the first N1 rows of H to be corresponding to those frequencies. And then let us say that the remaining rows of H correspond to the stop band. And so the remaining rows are defined by WF of NK. This WF K notation is same as what we have used before, except before this K was N. These complex exponentials were having N samples, capital N samples. Yes, Bhavesh? Bhavesh, you have a question?
No, sir. Actually, my internet went off for a while in between. That's
Okay.
why it got disconnected for a long time. Sorry.
Okay, fine. So, so this H matrix, if you look at individual element of H, it looks a lot like the individual element of W. It is exponent of J2 pi K times N, where K is the frequency, N is the time index. But the main way in which H differs from W, where W is this matrix we defined at the start of this lecture. In W, these complex exponentials are forming the columns. And there are a total of K such columns. Each column has a length of N. In this capital H matrix, I'm taking this column vectors, and first of all, I'm making them row vectors. And because the matrix has total of capital N rows, there will be total of N such row vectors. Each row vector will be one such W. And the length of the row is capital K. So that's why here I have said that these W's are having the length of K, and they are organized in the row by row manner. That is why this Hermitian transpose is there. But the point is that once I'm given the specification of what are the frequencies at which I need high response of the filter and what are the frequencies at which I need filter to cancel out the incoming signal, then I can formulate H because I know these complex exponentials. And so therefore my system equation looks like this. Let us look at this, what this equation is telling us. This is a row vector. It has a size of k. This is my filter vector. It has also size of k. So I can take dot product of the first row with the filter. And I'm saying that when I take that dot product, my output should be 1. Because I want to pass the signal, whichever signal it is, I want to pass it at this frequency f0. And so this is 1. This is my desired output vector, D. Then I go to the second vector. Even at this frequency, I want the filter to pass the signal. And so that's why I have 1 here. I have total of N1 frequencies in the pass band. And all of those I am collecting in the first N1 rows of this matrix H, which is what is shown over here. And so there are a total of N1 ones here in this vector D. For all the other row vectors, I want the filter to null out the interferences. So all of this is 0. So D is an n cross 1 vector. H is n cross k and W is k cross 1. And so this becomes my equation. Does this make sense? Are you getting it, what I'm saying here? Okay, Divya, are you there? Okay, does it make sense, this equation 7? Okay. How about you, Soumya? Are you there, Soumya? Okay, so I'm getting a lot of yeses, so hopefully this is making sense to you. Nemishi, is this okay? Okay. So now what you will see is that this equation D equal to H times W is same as equation 2. Actually, it is noiseless version of equation 2. What is equation 2? It is this equation. It's noiseless version, so I actually don't have U at all. X is now what? What is X? X is a vector of ones and zeros. It is this D vector.
D.
W became H. It's sort of like W, except as if I did Hermitian transpose on W. Well, no, I shouldn't say Hermitian transpose, but it is as if I use this individual W, F, N vectors and I made them row vectors. And what is this vector S? Yeah, vector S has become small w. What is small w? Who can tell me that? Let me see. Who all are there? So common small w.
Hello. The
Yeah.
small w you defined as the filter vector.
Okay. So
That
small w is the filter coefficient vector that I want to determine. In the previous analysis, we wanted to determine S. So now I'm directly determining the beamforming coefficients here. So it's kind of equivalent, but instead of doing the signal detection by beamforming, my goal is now to say what would be the best way to form the beam. So this is completely equivalent to that other model that we have been looking at. And so therefore we can use the same technique. We first define the correlation matrix. Remember I told you that I'm not putting any subscript. It's still R. But now R is not W Hermitian W, it is H Hermitian H. Sorry. Yeah. Right. So previously we defined R as W Hermitian W. Now it is H Hermitian H. What will be the dimension of R, Kishan?
Hello, sir.
Yeah. What will be
Sir,
the dimension of R?
N cross N.
No, it is going to be still K cross K. Yeah, Divya, you're right. Because remember, H is completely identical to W, even in terms of size. And W was N cross K. So H is also N cross K. So this is still going to be K cross K matrix. Then I will do this calculation of sufficient statistic vector Y. And so I got Y is equal to R times W. And then I will do either decorrelation or MMSE. And I'll get the beamforming vector back, W. Now remember here, there is no noise. So technically, decorrelation and MMSE become identical. But that is where the trick that Anudeep and Joel have been playing around with comes into help. Many times in their algorithms, this R is not invertible. And so they happily put this identity matrix and they put some small delta around it. And then it still works. Okay, so this was one more application that I thought we would look at. A completely different framework, but it ends up having exactly the same solution approach. We are going to look at few more such system problems that on the first hand or on the first sight appear to be very different. And then we will end up finding that we will be able to solve the problem using the same three-step process. Step one is to define the correlation matrix. Step two is to do this pre-processing, and step three is to do the matrix inverse. So we'll be using the same three steps on a few more problems when we meet next time. Okay, so I will be ending the lecture here right now.